Hello students, welcome to Basic Electronics, video 7, module 1. In this video, let us discuss the positive feedback and application of the positive feedback. In the previous videos, we have discussed the negative feedback which is used in amplifiers. Let us see what is positive feedback. If the input signal is like this, and if the feedback signal is like this, then we say there is no phase shift at all. There is no phase shift. Our phase shift is 360 degrees or 0 degrees. And these two signals aid each other. They reinforce each other. And they add together, and this V in dash, this is V in dash, this increases, input increases. If the input voltage applied to the amplifier increases, the output increases. The increased output is sampled, then once again applied as the feedback signal, so it goes on increasing. So it is regenerative feedback. So the output will keep on increasing. So when the input signal and the feedback signal are in phase, then we call it as a positive feedback. The output is fed back in such a way as to reinforce the input. Reinforce the input is known as the positive feedback. Otherwise, you can understand if both the signals, the input signal and the feedback signals are in same phase, then we can call it as a positive feedback. Here in this diagram, the basic amplifier provides 180 degree phase shift and the feedback network provides 180 degree. So in this loop, the overall phase shift will be 180 degree plus 180 degree. It is 360 degree. 360 degree is nothing but 0 degrees. So the feedback signal will be in phase with the input signal. So they aid each other. They will get added and the input increases. So that is the meaning of reinforce or regenerative feedback. Coming to the circuit diagram, this is the basic amplifier. This is the basic amplifier whose voltage gain is AV. And if this is a transistor amplifier, this provides 180 degree phase shift. Let us assume the input to this basic amplifier is V in dash. In your textbook, in the downloaded notes from the VTU, here there is a mistake. It is not V in. V in is the voltage to the overall amplifier with feedback. This is the amplifier with feedback amplifier circuit. For this is the input. V in is the input and this is the output. Then the overall voltage gain G is given by the output voltage V out divided by the input voltage in V in. This is the gain with feedback. I hope you understand. I are following this. So this is the feedback amplifier. For this overall feedback amplifier, this is the input and this is the output. Gain is nothing but output by input. But if you consider the basic amplifier, here the gain is, voltage gain is AV and its input is V in dash. You make these changes in your notes. Now this basic amplifier input voltage is this V in dash and the output is V out. Then the output voltage, some portion of the output voltage is sampled by a feedback network whose feedback ratio is beta. And this feedback network is designed in such a way that it also provides to 180 degree phase shift. So here 180 degree by the basic amplifier, 180 degree by the feedback network, total 360 degrees. So the waveform appearing at this place will be in the same phase with the input voltage. Let us see how. Here is the positive terminal and here is the negative terminal. The same voltage is applied to the basic amplifier. As there is a 180 degree phase shift, this terminal will become negative and this terminal will become positive. And here we are sampling the voltage. Here positive remains a positive. Here negative voltage remains at the negative. But as there is a 180 degree phase shift provided by this feedback network, here the polarities will become opposite. Positive will become negative, negative will become positive. The same negative is applied here, same positive is applied here. The voltage is fed back. Now what is this V in dash? What is this V in dash? V in dash is equal to the input voltage V in plus the voltage fed back at that point, beta V out. Because if you apply the input like this here, he will get inverted because there is a 180-degree phase shift. Some portion of this is fed back, and also see here there is a 180-degree. So once again it gets inverted. So what you can see here is a signal which is of the same phase. So they add each other. So input voltage V in dash is nothing but sum of the input voltage and the feedback voltage, or you apply the Kirchhoff's voltage law. If you apply Kirchhoff's voltage law, this V in dash is equal to, here minus plus minus plus, so sum of these two voltages, plus minus, so they add together. So this will be equal to this V in dash. So that is what I have written here. V in dash is equal to beta V out. Then what is V in? V in is equal to V in dash minus beta V out. Then this basic amplifier voltage gain AV is equal to output voltage V out and its input voltage V in dash. From this we can write V out is equal to AV into V in dash. Also you know the overall voltage gain of this feedback amplifier is given by V out by V in. Now substitute for V out and V in from this equation. Let us see in this slide. The same network is redrawn here. Overall voltage gain is G is equal to V out by V in. V in dash is equal to V in plus beta out. Let us call this as equation A. So from equation 1 we can write V in is equal to V in dash minus beta V out. Then V out is equal to AV into V in dash. So that also in the previous slide we have seen. So substitute equation 2 and 3 in equation A. So here you will get, in place of V out we have written AV into V in dash. In place of V in we have written V in dash minus beta V out. Now for V out, again substitute equation 3 for V out. Then in this expression take V in dash common, it will get cancelled. Finally what is remaining here is the overall voltage gain of this feedback amplifier is AV divided by 1 minus beta AV. If you remember, in the negative feedback G is equal to A by 1 plus A beta in the negative feedback. But in the positive feedback we got AV divided by 1 minus AV into beta. What are the conditions for the oscillations? Oscillations to be generated, what are the conditions? The first condition, the feedback must be positive. What is the condition for feedback must be positive? In that complete loop, the overall phase shift should be 0 degrees or 360 degrees. The overall phase shift around the loop should be 0 degrees or 360 degrees. That means the input signal and the feedback signal should be in same phase. That means the feedback must be positive. If both are in same phase, then we say it is positive feedback. So the first condition is the phase shift around the loop must be 0 degrees or 360 degrees. Or in other words, you can call it as the feedback must be positive. What do you mean by the feedback must be positive? The signal fed back must arrive back in phase with the signal at the input. The feedback signal should be in phase with the signal at the input. Then let us see what is the second condition. The overall loop voltage gain must be greater than 1. The overall loop voltage gain A beta must be greater than 1. So if you remember these two, then definitely you can write these sentences. A beta is nothing but the overall loop voltage gain. So A beta must be greater than 1. That is, the amplifier's gain must be sufficient to overcome the losses associated with any frequency selective feedback network. So you should remember these two conditions. Assuming that the amplifier provides 180-degree phase shift, the frequency of oscillation will be that at which there is 180-degree phase shift in the feedback network. Amplifier provides 180-degree phase shift and the feedback network provides 180-degree. 180-degree plus 180-degree is nothing but 360, which is nothing but 0 degrees. So both the signals will be, feedback signal and the input signal will be in the same phase. So that is nothing but the positive feedback. So to get this, there are number of circuits. They provide 180-degree phase shift, and one of the simplest being 3-stage CR ladder network. The feedback networks, there are a lot of feedback networks which provides 180-degree phase shift. Here in your syllabus you have a 3-stage CR ladder network that we will see in the next slide, which provides 180-degree phase shift. Original 180-degree phase shift will be provided by the amplifier. Then remaining 180-degree will be provided by the feedback network. So that will be a 3-stage CR ladder network. Or alternatively, we can select an amplifier which provides 0-degree phase shift. Then the feedback network should also provide 0-degree phase shift. Then overall phase shift will be 0 degrees. If the amplifier provides 180-degree, then feedback network should provide 180-degree. If the amplifier provides 0-degree, then the feedback network should also provide 0 degrees. 0 plus 0 is 0 degrees. So in both the cases, either in this case or in this case, totally 360-degree phase shift, here totally 0-degree phase shift. In both the cases, the essential point is that the feedback should be positive, so that the output signal arrives back at the input in such a sense to reinforce the original input. So if this is the input and this is the feedback signal, this will reinforce the input because they both add together. Now let us see the ladder network oscillator. The ladder network oscillator or the simple phase shift oscillator based on 3-stage CR ladder network. So this is a phase shift oscillator which is based on 3-stage CR ladder network. The transistor TR1 operates as a common emitter amplifier stage. This transistor is used as an amplifier, common emitter amplifier, with R1 and R2 providing the base bias potential, and R3 and C1 providing the emitter stabilization. If you have forgotten the terminal names, this is the emitter terminal, this is the base terminal, this is the collector terminal. So emitter is common for the input as well as the output, so we call it as the common emitter configuration. So R1 and R2 provides the base bias potential, R3 and C1 provides the emitter stabilization. The total phase shift provided by the CR ladder, this is one CR ladder, this is second CR ladder, this is a third CR ladder. So this is a 3-stage CR ladder. Each CR ladder network provides 60-degree phase shift, 60 plus 60 plus 60. Totally it is 180 degrees. 180-degree phase shift is provided by this 3-stage CR ladder network, which is connected between the collector terminal and the base terminal of the transistor. The transistor provides the additional 180-degree phase shift. So this 180-degree, totally it will be 360-degree phase shift. So this is one of the conditions to generate the oscillations. So totally 360 degrees. Then what is the frequency of oscillation at which this generates this 3-stage CR ladder phase shift oscillator? The frequency of oscillation is given by 1 by 2 pi into root 6 into CR. The unit is hertz. So you need to remember this frequency of oscillation f is equal to 1 by 2 pi into root 6 CR. So here same values of capacitance we have used, same values of resistances. Let us go through a simple example. Determine the frequency of oscillation of a 3-stage ladder network in which C is equal to 10 nanofarads and R is equal to 10 kilo ohms. As you know, F is given by 1 by 2 pi into root 6 CR hertz. So just substitute for the value C and R. C is equal to 10 nanofarads and R is equal to 10 kilo ohms. So if you substitute and calculate, you will get 647 hertz. Now let us go to the next oscillator, that is a Wien bridge oscillator. Wien bridge oscillator. This is a Wien bridge network. Here we have a series combination of R and C, and here we have the parallel combination of R and C. R1, C1 are in series, R2, C2 are in parallel. An alternative approach to provide the phase shift required is the use of a Wien bridge network. Earlier in the phase shift oscillator, we saw 180 plus 180, 360 degrees. In the Wien bridge oscillator, let us see, this provides 0 degree phase shift, and this is connected to a amplifier which provides 0 degree phase shift. 0 plus 0, it is 0. Like the CR ladder, this network provides a phase shift which varies with the frequency. The input signal is applied between A and B. The input is applied between A and B, while the output is taken from C and D. At one particular frequency, the phase shift produced by the network will be exactly 0. At one particular frequency, the phase shift provided by this network will be exactly 0. So if we connect this network to an amplifier which provides 0 degree phase shift, which has a sufficient gain to overcome the losses of the Wien bridge, oscillations will start. So this provides 0 degree phase shift. So if you connect this to an amplifier which is also providing 0 degree phase shift, then oscillations will start. The minimum amplifier gain required to sustain the oscillation is given by, you don't have any derivation, so directly we will take the expression. Voltage gain is equal to 1 plus C1 by C2 plus R2 by R1. Suppose C1 is equal to C2, if both are equal, so they get cancelled, so 1. R1 is equal to R2, here you will get 1. 1 plus 1 plus 1, it is 3. So the minimum amplifier gain will be 3. The frequency at which the phase shift will be 0. The frequency at which the phase shift will be 0 is given by F is equal to 1 by 2 pi into square root of C1 C2 into R1 R2. Suppose if R1 is equal to R2 is equal to R, C1 is equal to C2 is equal to C, the frequency at which the phase shift will be 0 is given by F is equal to 1 by 2 pi square root of C square into R square. So if you simplify, F is equal to 1 by 2 pi CR. Let us take a simple example. This is a Wien bridge oscillator, rewritten. This is the same as this network, this network, but it is rewritten like this. So this provides 0 degree phase shift. So this is connected to an amplifier. You can see an operational amplifier. This is connected to an operational amplifier which provides 0 degree phase shift. 0 plus 0, it is 0. So there is a positive feedback. So it produces oscillations. So this figure shows a Wien bridge oscillator based on the operational amplifier. If C1 is equal to C2 is equal to 100 nanofarad, determine the output frequencies produced by this arrangement when R1 is equal to R2 is equal to 1 kilo ohm. R1 is equal to R2 is equal to 1 kilo ohm. In the Wien bridge oscillator, the frequency of oscillation is given by 1 by 2 pi CR. C is 100 nanofarads, R is 1 kilo ohm. So if you substitute, you will get 1.59 kilohertz. In part B, that is when R1 is equal to R2 is equal to 6 kilo ohm, just change the value of R to 6 kilo ohm. See what is the value we are getting, it is 265 hertz. When R1 is equal to R2 is equal to 6 kilo ohm, it is 265 hertz. But if you change the value of R to from 6 kilo ohm to 1 kilo ohm, see the change in the frequency, it changes to 1.59 kilohertz. Thank you.